Hello, welcome to Numeristical. This is going to be part 3 of the 3-part series on classification, a discrete probabilistic point of view. My name is Brian Lucena. So let's get started. So we talked about a classification framework that we're going to use where we have predictors X and a target Y. And our paradigm is that we get some training data, we use that training data to build a model, and then we use that model to make predictions. And in the previous parts, we talked about what is a prediction, defining what we mean by that, what is training data, what we mean by that, and how we represent it, and what notation to use for it. And now in this part 3, we're going to talk about what is a model. So what is a model? Let's do a little bit of a review, though. So in the first part, we talked about this probabilistic approach, where what we want is, given a value of X, given our predictors, we want to predict a probability distribution on Y. So we're not trying to predict the exact answer of Y. We're really trying to predict a probability distribution on Y. And in the second part, we talked about what I call this discrete assumption that says that there are finitely many possible values of X, and therefore we can just list them. And that's going to come in handy, as we'll see, for the representation of the model. Now, so what should the model be? Well, the model is going to be this mechanism, therefore, that says when you give me a value of X, what is the probability distribution on Y? So a model is going to be a mapping from the possible values of X to probability distributions on Y. Now that sounds pretty complex and abstract, but what we're going to show, thanks to this discrete assumption, is that we can conceptually represent a model by what I'm going to call a conditional probability matrix. So if you think about it, a probability distribution on Y is just going to be a set of numbers that add up to 1, where each number represents the probability of a particular value of Y. And typically, for classification, the number of possible values of Y is relatively small. Now, since we have finitely many possible values of X, we could think about representing that probability distribution on Y for a particular X as a row. And then if we stacked up all these rows, we would get a conditional probability matrix. So I'll go ahead and define that a little more clearly in what comes next. So first, let's review some notation so we're all on the same page. So M is going to represent the number of possible values of X. So again, from part 2, we said we're always going to assume that there's finitely many, and we gave some justification for that. So call the number of possible values of X, call that M. Let K be the number of possible values of Y, so how many classes we have. If it's binary classification, K is going to be 2. If it's multi-class classification, K is going to be the number of classes. And then just use some notation to note the set of possible values. So script X is going to be this set of possible values. Script Y is going to be the set of possible values of Y. And therefore, the size of script X is M, and the size of script Y is K. So what I'm going to call a conditional probability matrix represented by Q is an M by K matrix. So we're going to have M rows corresponding to the M different possible values of X, and we're going to have K columns representing the K different possible values of Y. And a particular entry in this matrix, so that little qij, which is the number that's in the ith row and the jth column, is going to represent for our model, what's our model's predicted probability that Y equals J given X equals I. So another way to think about that is each row is a probability distribution on Q. Each row is a set of numbers, which are probabilities, which sum to 1. And that represents the distribution of Y given the value of X. So let's give a quick example to make this concrete. Suppose M is 5. So let's say there's just 5 different possible values of our predictor. And K is 3. There's 3 different values of Y that we're trying to get the probability distribution over. So here's an example of a conditional probability matrix Q. So imagine we do some modeling, we get some data, and our model predicts that when X is 1, we're going to be on that top row, and the probability of Y is going to be 0.1 for Y equals 1, 0.8 for Y equals 2, and 0.1 for Y equals 3, and so forth. So you'll see each row sums to 1, and each number is a probability, and the probability represents, given that my value of x is the particular value corresponding to the row, what is the probability distribution on k? And I want to point out that this is an m times k minus 1 dimensional space. So what do I mean by that? Well, because the rows must sum to 1, if I just gave you the first two columns of this matrix, the third column is already defined. I have no flexibility in defining the third column once I've defined the first two columns. So really, the number of dimensions is m times k minus 1, because once I fix the first k minus 1 columns, the kth column is just a function of those previous columns. So in this case, where m equals 5 and k equals 3, I would actually have a 10-dimensional space. It would be 5 times 2. So let's summarize the process that we've defined now over the past 3 videos. The universe has some joint distribution, p of x comma y, and we can think about factoring that into a probability on x and a probability on y given x. And what we're concerned about is estimating the probability of y given x, because we want to make predictions. So we're going to be given x's in the future, and we want to know what can we say about y. So our goal is to estimate the probability of y given x. Now, we can use this idea of a conditional probability matrix to represent the truth as well. So we can say that the universe has a set of numbers that it uses to generate the y after it's generated the value x. And we can represent this matrix by t, and we could say that tij, the number in the ith row and the jth column, represents the true probability that y equals j given x equals I. So we can think about this as we really want to learn what is that matrix T. That's our goal. So we get training data that comes from this joint distribution that the universe has picked. And we build a model from that training data. So that model could be anything, could be a neural network, could be a random forest, could be logistic regression, whatever it is. We build some model, and our model can also be represented by a conditional probability matrix. We're going to call this one Q. And similarly, Q is a set of numbers that represents our model's predictions for the probability that y equals j given x equals I. So Q is our estimate of T. And that's how we can really frame the entire classification problem. Now, we talked about that our goal is to estimate the probability of y given x, and that we're not really paying too much attention to the distribution of x itself. And this is an important thing to keep in mind. The model is not attempting to represent the probability on x. So let me try and frame this with a real-world example. Suppose you're making a prediction about hospital patients, and you want a model that says, given the age of the patient, what diseases they have, their lab values, and so forth, we want to predict what's the probability they're going to die in the hospital. So our model is not attempting to estimate what are the population characteristics of the hospital. We're not trying to estimate that. We're just trying to predict what happens to these patients. But the distribution of patients that come into that hospital is going to influence our process in a few ways. So the first way it's going to influence us is that we're going to have more training data at some values of x than others. So if we have a hospital that mainly serves older patients, and our distribution that the universe has picked, this px comma y, is such that p of x is skewed toward older patients, we're going to have a lot more training data value at, say, older patients than younger patients. And what that means is our model is going to be more accurate in estimating the predictions for the older patients versus the younger patients. And so to put it in more mathematical terms, those rows of T is the truth, and we have corresponding rows in Q that we're trying to estimate. Our estimates of certain rows are going to be more accurate because we have more data about them. Furthermore, the metrics that are typically used to evaluate performance, that's both to fit the model and also to evaluate how well we think the model is doing, are going to value predictions at the more common values more than at the rare values. And in future lectures, we're going to go into evaluation of models, and we'll be able to dig into the math and see how and why this happens. But it's an important thing to realize that the metrics that are commonly used essentially say it's more important to get the things that I'm going to see very frequently right. And it's less important to get the things that I'm going to see very rarely right. And on a very broad level, this makes sense. We want to do well on the things we're going to be doing every day, and we're less concerned if these really unlikely situations, if we don't do as well on those. But this has a lot of implications for fairness and ethics, and there's been a lot of discussion about this in the media today. And one of the implications is that this probability distribution on X, the demographics of our training data, is going to essentially say that we are less concerned with doing a good job on the things that we see more rarely. And while this may make sense in a lot of mathematical contexts, there are a lot of social contexts where this may not be desirable. And often the training data is not a good representation of the reality that we really want to predict. So this is a really important thing to keep in mind, and we'll be talking about this in future videos as well. Okay, well, thank you very much for listening. Please like and subscribe if you haven't already. We'll be building out a lot more content on this channel. The next set of videos is going to be around how we evaluate models. We're going to talk about things like maximum likelihood, log loss, entropy, and the connections between all of those concepts. Please leave a comment below if you want to start a conversation. And likewise, please make an account at numeristical.com. You'll be added to the mailing list, and you'll be able to participate in our live events via our Slack channel when those occur in the future. Thank you very much, and have a great day.